In this video, we're going to be talking all about the mean value theorem. The mean value theorem says that if a function is continuous on the closed interval a to b, and it's differentiable on the open interval a to b, then there must exist a number c such that the derivative at c is equal to f of b minus f of a over b minus a. What this is basically saying is that the instantaneous rate of change is equal to the average rate of change at some point. Sometimes I think this helps to think about it in a real life example. So imagine, write this out here, it takes you 1 hour to drive 20 miles. That would tell us that your average rate of change, I'm going to abbreviate that here, AROC for average rate of change, is 20 miles per hour. Okay, so on average, it took you 1 hour to drive 20 miles. What the mean value theorem is saying is at some point C, so at some time, in an exact moment, you are going exactly 20 miles per hour. So if you think about, let's say you're driving to work and you work 20 miles away and it takes you that 1 hour. Okay. At some point, you had to be going exactly 20 miles per hour, and that is your instantaneous rate of change, abbreviating that with IROC here. So again, at some point, you had to be going exactly 20. Maybe sometimes you were going higher than that and you were on the parkway. Maybe sometimes you were stopped at a red light. But at some point, if your average rate of change was 20 miles per hour, you had to be going exactly 20 miles per hour. And of course, there's the possibility that there are multiple values of C that this would apply for. Now, Rolle's theorem is essentially a subset of the mean value theorem. It says that if a function is continuous on the closed interval and differentiable on the open interval, so similar prerequisites to the mean value theorem, then there exists a number where the derivative at c, so f prime of c, equals 0. This is basically telling you that the average rate of change is 0. And then let's just recall a derivative of 0 indicates that there must be a horizontal tangent line. All right, let's take a look at some practice questions to see what some things would look like that regard mean value theorem as well as Rolle's theorem. So number 1, given the function f of x equals x squared plus 5x plus 6 on the closed interval 0 to 3, when is the instantaneous rate of change equal to the average rate of change? So notice it doesn't specifically reference the mean value theorem, but that idea of instantaneous rate of change and average rate of change being equal. And we know that we have this closed interval here. That's going to be referring to mean value theorem. We should also just keep in mind that this is a parabola. Parabolas are always continuous and they're always differentiable, so it does meet those requirements of the mean value theorem. So let's write down our basically our formula that we're going to use for mean value theorem that says that the instantaneous rate of change and the average rate of change are equal at some value. Now the derivative f of x would be 2x plus 5. Over here, we're essentially finding the slope. Average rate of change is slope. We are given the x values of coordinates. So I'm just going to jot those down over here. We are given the interval 0 to 3. Those are referring to x values. So we have to find the y values that correspond to that. So I can do that by plugging 0 and 3 into f of x and getting our output from there. Once I have those 2 points, I'm going to plug them into the slope formula over here. And when I simplify this a bit, I'm going to get 2x plus 5 equals 8. Now remember, we're trying to find the value of c, so we could write this also as 2c plus 5 equals 8. And if we solve this, we would get 2c equals 3, or c is equal to 3 over 2. So that means when x is 3 over 2, the instantaneous rate of change and the average rate of change are equal to each other. Okay, for number 2, given the function f of x equals x cubed plus 6x squared, we're going to find the value or values of c that satisfy Rolle's theorem on the closed interval -6 to 0. So we are going to set the derivative. So that would be 3x squared plus 12x. We can use power rule to get that, equal to the average rate of change. Now, again, since we're using Rolle's theorem here, we are going to set this equal to 0. Okay, but if we did plug in -6 into the function and we plug 0 into the function, that slope would come out to be 0 as well. All right, to solve this, we could, again, replace x with c since it's asking for c here. And we're going to factor out 3c. And when we solve on both sides, we're going to get c equals 0 and c equals -4. Both of those values are in the interval -6 to 0. We always want to do that quick double check that they are in the interval. So our answers would be both of those values, -4 and 0. Number 3, given the function y equals the square root of 5x, find the value of c that satisfies the mean value theorem on 0, 5. All right, so let's find our derivative. So if it helps to think about this, we could rewrite this as y equals 5x to the 1/2 power. And when we find the derivative of that, we are going to bring the 1/2 down, subtract 1 from the exponent, and this is a composite function. So we're going to multiply by the derivative of the inside, so multiply by 5. And we're going to set that equal to the slope. Now remember, we are just given the x coordinates here. We have to find the y coordinates. If I plug 0 into the original function, I get 0. If I plug 5 into the original function, I get 5. So when I find the slope over here, this will simplify to 1, and I'll write that in just a moment. So I'm going to clean up this left side a little bit. It looks a little messy here. So I really have 5 over 2 radical 5x is equal to 1. We could even put that 1 over 1 so that we could cross multiply here. So I have 2 radical 5x equals 5. And now let's solve algebraically to get x by itself. All right, so I squared both sides to get rid of the radical. Then I'm dividing by 5. So I have x equals 25 over 4 divided by 5. And if I simplify that, that is going to give me 5 over 4 as our value of c. All right, let's take a look at number 4, a bit of an application question. It says the height of a tree at a time t in years is given by a twice differentiable function, h of t. Let's just recall for a second here before I even continue that if a function is differentiable, that tells me that it's also continuous. So I'm going to have to reference that in a little bit. H of t represents the height of the tree, and we have select values given to us in the table here. So part A, for the closed interval 1 to 10, does a time t exist such that h of t equals 13? And then we're going to explain this here. So I noticed something different about A, and if I even glance down to part B, A is talking about the original function, which is the height of the tree. B is talking about the derivative, okay, how it's changing. So on A, we're essentially saying, is there a time where the height is 13? I can glance at the table of values here and imagine that somewhere in here, the height was 13, right? Somewhere between 5 years and 8 years. And I know that that's going to work because as we established previously, this function is continuous. So this is really referencing the intermediate value theorem. So here's how I'm going to write this. I'm going to say since h of t is differentiable, it must also be continuous. Let's get those requirements out of the way. And that's on that interval 110. Now let's talk about why we know that there is a value of h of t that is 13. So I'm going to write since h of 5 is 11, and h of 8 is 15, according to the intermediate value theorem, a time t must exist where h of t equals 13. We could think about intermediate being something in the middle, right? When you're skilled at something, there might be a beginner level, an intermediate level, and an advanced level. Intermediate is that middle. So we know that 13 is in between 11 and 15. So we know there has to be a time t between 5 and 8 where that height of 13 occurs. Now, when I look at B, it says on the closed interval 1 to 10, does time t exist where h prime of t equals 4 over 3? This is now referencing mean value theorem. The way that I know that is because I have that derivative notation in here. So that makes all the difference, and we have to read that carefully. So let's start by just talking about those requirements of mean value theorem. So I'm going to repeat some of the stuff from part A. So I'm going to say since h of t is differentiable, it must also be continuous on 110. So the mean value theorem applies. Now that we've got the requirements out of the way, let's talk about where this 4/3 comes from. So I noticed that actually in those same values that we talked about in part A, if I find the slope between those 2 points, 511 and 815, it comes out to be 4 over 3. So I'm going to talk about that. That's our average rate of change, right? The slope is average rate of change. So I'm going to say since the slope between t equals 5 and t equals 8 is 4 over 3. There must be a time t where h prime of t also equals 4/3. So essentially, since there's a time period where the average rate of change is 4/3, there also must be an instantaneous rate of change where the change in height of the tree is equal to 4 over 3.